My name is Marek Kowalski. I'm a CTO and an owner of a software house company. We offer software development services to our clients. I've been doing this for 10 years, I guess, give or take. And our specialty is EVM blockchains and AWS. So AWS helps us winter, whereas EVM is for summer. So there is 4-year cycle. You probably know this. Everybody knows this. So in my normal day work, we offer software development services, and this is what keeps company working and pays salaries and everything is running. But a software development company cannot be at 100% capacity dedicated to work of clients, because if we did that, we would never start a new project, because you cannot just hire new people for a new project and say it to a client. This would be a disaster. So the strategy for a company has always been that we have some spare capacity which we can use to do cool stuff. So today I'm just talking about this cool stuff. I will be talking about a passion project of ours which spun out of control, and now I have interesting things to talk about on events like this one. So the topic is what to do when transaction reverts, and the reason is swallow. So why do I mean by the swallowing part? So I selected this particular piece of code, and I would like to ask you if any one of you in your debugging have ever come to this save ERC20 low-level call failed. Is this the first time you guys hear about it? First time? Everyone? Okay, so this is like a private joke in my team, because back in 2020 we were working on this project which was not on Ethereum mainnet, it was on some testnet of sorts, very bad explorer and really no visibility. And when stuff failed there, you were really left in the dark, and this hunted us. So can anyone tell me what library this code is from? OpenZeppelin, exactly. So this is Safe ERC library. It sort of wraps a token code which is unknown code. So it's recommended by Zeppelin to interact through this wrapper. But it does one thing which drives me crazy, and literally there was one guy in my company who quit the job and said that this is because of this error. This is how frustrating it is. He just changed job and now he's a game developer, and he just left blockchain entirely because of low-level call failed. I think even his therapist knows about this error, I would assume. So this is hardcode solidity, so this func call data, it just passes call data to some other contract, but then it's sort of whenever there is an error, just return this error. But it hides what the original error has been. And we've been integrating this Aave with Balancer, and these two protocols didn't play well, and the tokens refused to transfer. Really it was because there were problems, but then knowing what these problems are really helps you debug these problems. So a lot of time we were battling against the server. So now a quiz question: what do you do from here? If you get this error, you seem to know this stuff. What would you do?
Usually what I try to do my debugging is print, right? And this is the best thing, because that's the straightforward, but console.log some stuff. Trying to go, because it seems, so it all goes down, the idea was the safe was proposed by OpenZeppelin to provide some safety about the transfer call or something. But I've been studying this just recently, but the thing is, this is embedded in so many levels that you keep laws of where the error is
Yeah.
and where you should look. And I know that because I also come from a Java world, and when you have interfaces and stuff, and on this level, I'm not 100% sure how you can do for the debugging, but yeah, if I need to look, I'm thinking out loud, but you can maybe do some taint analysis, or if you can go that far, but to do that debugging, I'm not. Yeah, you would need some kind of a debugger, but that's why I came here. Because
Yeah, exactly. So, but like your first idea was great, and we even have a name in this in Polish. This is called metoda przesuwające się dupy. I don't know if it translates well in Slovakian. No. So it's like a method of removing S. And this is because you do like print dupa, which is like print S. And this is a formal method of debugging that you employ to deal with this kind of errors. It's frustrating, it's time consuming, and this is something you talk with your therapists if you are expected to do this 8 hours a day, 5 days a week. So fortunately there is a better way, a more formal way. Okay, you know what? I will put the light out because this is. Okay. Is it better?
Yeah.
Okay, great. So, so there is this RPC call which is called debug trace transaction, and what it'll spit out is quite a big of file. Like here is like what Emacs tells you when you try to open a file like this. So it tells like, hey, this file is 100 megabytes of text, like, are you sure? And if you say, yes, I'm sure, like, probably your computer will start, swapping, and everything will get clunky. And this is, like, below, it's roughly how this file looks like. I mean, this is obviously a tiny part of it, but this is like a long list of JSON, and it has stuff like PC is like program counter, op is like what is instruction that happened, gas is like how many gas it costed. Oh no, sorry, gas is like how much gas is left, gas cost is how much it costed. Depth is about like when you go into like a contract calls contract, the depth increases, and then when it goes back it decreases. And three very important things: stack memory and storage. Like, so essentially this is all the states of a virtual machine step by step throughout the entire contract. And these files can get pretty crazy. Like it can go, like the biggest I've seen was 1.5 gigabyte for like, some, something using Uniswap and making some arbitrage trade. Like this can be, quite big. So what we did at some point, so I have this feed here. So this is like, I opened it up and then I needed to find revert reason. So like you are doing revert, or this will take a few seconds. Oh, or not.
Maybe lowercase.
No, it should be uppercase. Okay. So yeah, but essentially like using this file, like without any tool, you can pretty much just go through this file, and if you know how to look, you will essentially find some stuff. So like in this particular example, like this revert here, actually takes two parameters. So the two topmost stack parameters, like this 11 and this 27, this is actually in hex. One is offset and another one is length. So this means that if I now look at the memory bit, and if I start from 11 offset and I take 27 bytes, so if I were to copy this and then like decode it hex to ASCII, I would actually get something that makes sense. Again, if you're expected to do this 8 hours a day, 5 days a week, you are going to get in some mental problems quite soon. So that's not what I recommend. So I figured, there's a problem, and we spend so much time on this task that we should automate it, right? And there's actually, excusite about it. So I spent so much time on this task, I should write a program to this. So this this really tells the story of our project. So it's like the theory is that you will automate it, and then it will take no time at all. And the reality is that you like debug this, and then you develop a debugger, and then you are refactoring it, debugging, and then there's ongoing development. And this timeline here actually is cut short, and because we are on the right hand, because like after ongoing development, you actually hire people to continue the development, and then you go to events like ETHBratislava to talk about this stuff. And maybe what is next, maybe even, maybe it will get funded by Ethereum Foundation, and maybe this will be something serious, but it's very much a passion project. Okay. Oh yeah, so the solution is the EVM Debugger, meaning like, so this is this tool that we developed. There is a QR code, but I will tell you the address later. Okay, so I will show you how to use it, like in reality. So there is this transaction. I will show it on EtherScan. So this is the transaction this is not the transaction on EtherScan. This is a different one. Okay, so this one ends at 60. Yeah, so that's the one. So on EtherScan you have stuff like this. So you have some call to swap function on MetaMask router, and you know it fails. And actually before some, I think the merge, there used to be good view for this. So back in time when Ethereum mainnet was using parity nodes, there was something which was called parity trace, and it was doing quite a good job. But if you look here, you will not. You will just get an error that it's reverted. So I will now show you this same thing in debugger. Yeah, so that's the one. Okay, so first of all, how you use debugger? You go to like EVM Debugger, you put here transaction hash, and you process logs. This takes 3 to 5 minutes to get this displayed. The reason it takes so long is that we have extensive backend. We actually replay this transaction on a forked blockchain to generate this debug output. Then we fetch all the source code from EtherScan. We compile all this source code using write source version to generate source maps. And then we feed it into the analyzer, which, it's a lot of data, so it takes a few minutes. So because it takes a few minutes, I already have it open here, but like this is something you would see if you just did what I said. So it just goes and it's like compiling some sources, and it gives you some idea of what is happening in the meantime. And then you get to a screen like this, and this is really the most helpful screen. So you open this stack trace. And you can pretty much just see this error amount is not enough. But interesting thing is like we are able to deconstruct the entire tree of calls. So the original call is to metaswap router, but then it makes a call to this contract which sadly is not verified on EtherScan, and then it does some delegate call, and then it calls to some aggregation router and whatnot. So like call and delegate calls and static calls are calls to other contracts, so it starts internal transaction. But inside, you can also see internal functions. But in this particular example, we are interested in this error, and the easiest way to get to an error is like using this navigation. There are like some highlights of a transaction. So you can go to reverts, and you can click revert, and you are moved to a line which reverted. So on the right-hand side, we actually have solidity code of this contract. And on the left-hand side, we have these EVM steps. So this list is actually the very original file which I told you about, like that can have like a gigabyte of data. And on the top you have stack. So for example, here in revert, you can see that we labeled the topmost parameters. So the parameters consumed by this opcode are labeled. So we know that starting this offset in memory and this size, so actually it's highlighted in memory. So this is actually what is getting reverted. And in Solidity you can see that this is, this is this line. So now, like, we could actually go back in the steps just using the up arrow, and we can see, so the current statement in Solidity is getting highlighted. And for every step, you see what is happening on stack and on memory. So that's one thing. And one thing that I haven't said, like, you can ask me questions as well. So if something is unclear, you can just, you don't need to wait for me to ask if there are any questions. But maybe that's a good.
About the EVM steps on the left-hand side.
Yeah.
Does this show like every step in the
Yes.
contract you executed, right?
It's not in a contract, it's in transaction. So this is really, so this EVM steps, this is it. This is what we are showing here, right? So we are showing this in a browser, and therefore it's like more stacked.
Understandable, yes.
I have a question. So the thing is, the EVM is atomic, so it's a finite state machine.
Yeah.
It's proven, right?
Yeah.
Correct me if I'm wrong. So that's one thing. So I guess that building a debugger should be, in theory, more easier than for building for a regular language that would be that wouldn't be this narrow in some point of view. My question is, you have in regular debuggers, you have this thing about back in time debugging. So you can not
Postmortem.
only- yeah. So you can go like forward and backward.
Yeah.
Not all debugger can do that, and that's a really powerful feature from a vulnerability analysis point of view.
Yeah.
You can really narrow the path by going in time, back in time.
Yeah.
So can you do this with your interface here? Can you just go back in time, or is it just like backwards?
Okay, so first of all, this is history. This
Okay.
is a transaction that happened on a public blockchain.
Okay.
So this is already sealed. So we
Okay.
cannot change anything.
Okay.
However, what you do, what transaction consists of, it consists of a couple 100,000 steps.
Yeah.
So you can inspect every single step.
Yeah. Okay.
And you can, so here, when I'm in the steps and I'm using up arrow now,
Yeah.
so you can also see that in Solidity code I will be going, like upwards more or less, but sometimes in some functions as well. So this is what it does. And we have a lot of ideas what we will do later on with this interface. Like, for instance, you can see that if the local variables are still like something we want to tackle.
Yeah.
So we want to be able to show the values of them, but it's tricky. What we do have already, so for example, this, so we have, for example, there is swap, and it's it's still external. So what I mean is, like, we do have the coding of. I will show this on this other transaction that I prepared. No, sorry.
No, it answers my question. So thank you.
Okay. Okay, so there's one more example. So this was pretty simple. So you have an error. You can just pretty much see it in a trace and jump to it. So something a little bit more advanced is this one. Okay, so this one is like 35. So let me find it. Yeah, so this is the stuff. And maybe first on NetApp. Okay, so what is happening here? So this is a transaction. It's actually an old one, 2 years ago, but so what does it do? It used to show more here. Yeah, so it's just a transaction that succeeded. So now let's see it in a debugger. So maybe on this screen. So it's a well, maybe on this screen. So it's a call to claim code, and it's interesting that so it's some kind of a scheme where there's like an ICO with a Merkle tree. So essentially what we can see in here are a few interesting bits. First of all, like when you, so for example, when you see this, maybe I will make it a little bit bigger. So something that I find interesting, like for example, there's this verify function, and it takes an argument of call data. So I'm quite sure that all of you, or some of you who work in Solidity know that you can do something like accept call data parameter, but like with a debugger you can, for example, see what it means in practice. Sorry, it will be here. Okay, so for instance, there is this method, right? So it accepts the proof. So the Merkle proof is like a list of hashes. And like when I was thinking about like what is a good example of using a verifier, like maybe I'm in a situation where I'm trying to verify a hash, but it won't verify, right? So what I would like to do now, I would like to go through this process step by step. And for example, I have a code which is generating the Merkle proof on my TypeScript code base. And in my TypeScript code base, I can console log everything. Yet I deploy it to production, and then it doesn't work. So it just tells that the hash is different. So what I can do here? So so there are a few interesting bits which I find here. So you can understand what happens. Okay, so for instance, okay, hold on. What is happening here? Right, never mind. So, for example, we have a method here which iterates over an array. So if I put myself here, I can see that through this line there is 13 different passes, and it makes sense. Like it's a loop, it gets 13 elements, so I'm getting 13 times through it. So I can jump myself to where the pass through this line begins, and we can inspect step by step what really Solidity does. Well, not Solidity, but what Salt does. Like, what does it really mean for us to access proof from I? Okay? So there are a few steps, and this one is an interesting one. So this is mload, so it's loading something from memory. So now if we look at the memory bit, we can see that this part is highlighting. So it's a word, so it's like 32 bytes, and it has 0D, and 0D is like 14. So so at every bit it's like loading the size of array, and then once it has size of an array, it's checking if it's less than 1 in this case. So it's comparing 14 and 1 just to check if there is not an overflow of an array, and when it's not, it's calculating address in memory, and then it's doing another mload. So in this particular case, it's loading this byte from memory, and then it assigns it to stack. So it's putting this on the first element of a stack. So now if we jump a little bit further, this is this bit that I wanted to show you. Hold on, I will get to it. Yeah, so there is a call to Ketzak. So this would be a call which like we are really interested in when debugging something like this, because then in this ketzak we can actually see that it's doing a ketzak on offset and length, and also, oh no, it's not highlighted, but it's 413. So so this is what it's. So this is actually the preimage which it's passing to ketzak. So now, like if I were in a situation where my proof doesn't verify, like this is something I would check. Like I would load this code, put a breakpoint, inspect every passes, and at every pass I can see what it's passing to ketzak, what the ketzak is, and now I only need to go to other side, being like my TypeScript code, and just compare where things are different. And I wanted to show you one more thing here, but something has changed. Yeah. Okay. So this is this thing I wanted to show you. I will collapse it here. So yeah, there is a call to claim tokens, and it has a parameter called called data Merkle proof. And if we look at here, there are some things in here which looks a little bit odd, like this AVI, the code tuple, and all this stuff. So this is actually the thing that Solz is adding to our code bases. So it's sort of like a code which is always included in your contracts even if you haven't written them. And it's written in this language which is called YUL, which actually when I started I was not even aware it exists. So here we actually show this file, like utility YUL, and reading this file like really teaches you a lot about Solz, like more than you wanted to know. So for instance, for every pretty much type, they have a function like this, and you can learn from reading this how really internal complex types in Solidity are encoded. So in this particular case, we can see that this is a function. It takes head start and data end. So topmost parameters of a stack are parameters of this function, and then I will not go through this line by line. This could not be very entertaining for you, but this logic is about decoding an array. So an array in RLP encoding is like first word is offset, second word is length, and then the rest of words are the actual elements of a list. And the word is 32 bytes on EVM because it's 25/6 bits. So yeah, so you can even see stuff like this in this. So it's like very, under the microscope. And I have a third example, but maybe it's a good moment to pass for questions, if there are any, about this part.
I have a question. Sometimes, for example, we can print stack traces using Wake or Foundry, for example, like we can see what this transaction does with all staticals and calls, with reverts and so forth. However, as the same as for the coverage, for example, it is very difficult to do, like in your case, implement the debugger when the code is optimized. The code is so, because it's like a completely different set of instructions. It's not one by one to the code. So, and I guess these tools, because I guess there is a lack of information for such tools, because there are investigation tools like Falcon, for example, like they can show the stack trace, but they can show the call trace, I would say, between contracts. And if you use a debugger, for example, the optimized codes, I think it will not work, or does it work?
It does.
It does.
So the whole point is, and it's really sort of like a side effect of things how Etherscan engineered their solution. So to verify contract on Etherscan, you need to provide a source code and all the flags of your compiler.
Yes.
And Etherscan runs this version of Solz, outputs the bytecode. then it calls if get call at this address and compares it. Only if it's byte to byte exactly what it has given, it will verify your contract. This means that if you are dealing with a verified contract, you know that you can compile it exactly the same way. So this is what we are doing. The only thing that we are adding flags so that it also spits out the source maps. Do you know what source maps are? I didn't know. So
Just very briefly, maybe, because I heard about it.
okay, so it's compressed and whatnot. But if you get through all the layers of encoding and decoding and packing, what it really is, it's a mapping of ranges in a bytecode to ranges in a source code.
Yes.
And what you see in here, so this like 0, 1, E2, this is this PC argument, so program counter. So now we take this PC, we find a range in this mapping from source code, and we know which line or part of line this is. So this is really what we are showing in here. What is tricky though is like to reconstruct this view. This is really what you are looking at. This is again entire history of this transaction, but we have filtered in only calls, static calls, delegate calls, and the jump tests. So we have taken all the catags, mloads, sloads, all of this is just deleted. So now for every jump test, we are figuring out if this jump test is pointing to a function. And that's the whole trick. And then in this jump test, in the frame showing this jump test, so for example this one, okay, this one is complex because this has call maker data, but if you now look at stack, like the arguments here correspond with stack. So this is how we get these things. So, but for example, this is complex stuff because it's a call data parameter. So we only on a stack you only have an offset to call data. So we have to do a little bit of work to like know that we need to look at call data and load and then decode it from RLP as an array. But then you see entire bytes array here. It was a few weeks for one dev to shake it out of bugs, but now it works quite well. What we did not do yet, and it's on our roadmap, is to also decode structs, because like in Solidity you can also have like parameters which are like types, like struct, and these are not included in ABI, sadly. So to get shape of these structs, we need to parse Solidity in complex way. So we haven't done it yet because we don't have definitions of these structs, but we will get there. It's step by step kind of thing.
What about only bytecode when you don't have the source code? Can you?
Yeah. Like and this is actually, I think even in this transaction it happens. No, in another one it happens. I'll show you. Okay, so for example here, right? So this is a contract which is not verified. Like for this contract we can only show its address. We don't know its name and we cannot decode ABI. Well, we can decode ABI for typical stuff like ERC20, 721, like we have sort of like a database of signatures that we know about. But if it's something we don't know, like this is how we display it. And if we are to go into this code, this is what you will see. Like, no source code available for this contract. So then you are like left at this low level. And in this particular case, this is just a delegation proxy. So, and I know this because I read this. So delegation proxy is tiny, and you can pretty much just read through this. It will, just call data load and eventually just call. Well, it's coming. Yeah, so. Okay. trust me, this is just a delegation proxy. So in this particular case, this would be easy. But if there are really contracts when someone have not verified them, I mean, you have to be more comfortable with EVM itself to debug them. But on mainnet, like most people, verified their contracts. And if you are dealing with someone who's on mainnet and having verified contract, like what is his deal really? You know, like why did he not do this? Yeah. Any more? Or further example? Alright, so I have like last one. Last example. Yeah. So it says like 32 in the end. Hold on, not this one. Yeah. So that's the one. So this is actually something which is recent. Like last night, I learned that I have 1 hour for this presentation. Previously, I thought I had 30 minutes. So I found a transaction which I found interesting. So what is happening here? This is a call to account abstraction ERC3337 bundler, which is calling to entry point, and then we have this internal error, but that's pretty much all you know. And I can bet that someone who sent this transaction is scratching his head right now because it's 17 hours ago. So I don't think they figure out yet what happened. So let's see at the beginning of debugger what it will show you. Yeah, so that's the one. So what it will show you is something like this. It's a call to entry point handle operations. As I told you before, sadly we are not yet able to decode this user operation. It would be really cool to be able to do this, but you know, in time. But then it does, you know, stuff like verifying prepayment. So this is called with paymaster, and it's like taking funds, and then it's calling validate user op. By the way, who is familiar with account abstraction in this room? Right. So, like using a tool like this, you can really look into detail of what entry point really does, because I presume you haven't read the code of entry point. I mean, I know I haven't. And then, like, you get to this inner handle op, and this is the actual call to a wallet. So as you can see, the wallet has not been verified, which, I mean, it kind of makes sense that wallet is not verified, because like wallet is created from some factory, not from hard hat deployment script. So this is something you expect to not be verified. But then it's calling to universal router execute. So this is from Uniswap, and we have this out of gas kind of thing. Yes?
I know there's that functionality on ETHScan where the code is not verified.
Yeah.
It sometimes says that the bytecode is either exactly the same or similar to other addresses. So that might be an idea how we could try to load this.
Yeah. So this is actually interesting to look at this. Maybe that is the case in this particular situation.
If you go into contract.
No.
Yeah, the contract was.
No. So this is what it's showing really for this address.
We also found another 1,554 contracts with exact matching bytecodes.
Yeah, that would be right. So this is.
So any of them is verified. Of course, it's not that easy to check all of them, but if any of them is verified, you could like use the code.
So I think you're right, but I think this is what ETHScan does. I think if any of this 1,500 instances would be verified, I think we would have gotten the contract. So I think in this particular case, they just didn't care to do it. Yeah, that's what I think.
No, you're saying that if any of those were verified, the code would be here?
Yes.
I'm not sure, because it would be like ETHScan is doing the job of the person who verifies, right? So
well, no, I mean, so this person did the first one, right, and then it would follow. So really this is the first one, right? So if they have verified it, they would verify the first one, but the first one is not verified. So it's just like, in this particular case, they like, owners of this project have not just cared to verify. And you can tell by the length of this is not a real contract. This is again a delegation proxy. So delegation proxies are often just written in assembly, and they don't have a solid code which compiles into this assembly. So I think this is one of the reasons why this is not done. And actually, we could have fun with this bytecode. Like, why don't we decompile it using EtherScan, and we can have some idea of what it does, right? I mean, it's a delegation proxy which we can see, and then some error handling. But it does some special thing for an address which presumably is an owner.
Proxy. Admin transparent proxy.
Yeah. So yeah, we can have some idea what it does, but again, like debugger is not so helpful for contracts which have not been verified. But in this particular case, you get this is not the one. Is this the one? No. Okay, hold on. I'm lost in all my tabs. Is this the one? No.
I guess it should be the last or the previous one. It should be there, I think.
Yes, that's the one. So in this particular case, we can see that universal router execute was not passed enough gas. What is happening here? So this screen is another screen which I haven't shown you. I mean, arguably we need to work on this a little bit more, but what it shows you is like where you are using the most gas. So like the entire square is like your entire transaction, but you can like select a part of it and like see. So for example, this is this call to universal router, and you can see that it was passed this much gas, and the gas cost is bigger, so it has overflowed. So in this particular case, like when you are sending user operations, you need to specify these free gas parameters, so we just should pass more gas and it should work. But you can see this kind of things. Yeah, I mean, these are really the 3 examples I prepared. So maybe there are questions about this part too. Oh, now I don't see you.
There's one here.
One question.
Yeah.
Does it work only for? I see it supports multiple chains, I guess, or big chains or Ethereum right now.
So now you are poking where it hurts. So, like 5 days ago, there was a list in this dropdown, and there is this story that, like, I was even like considering canceling this presentation because, like, there was Cancun upgrade, which forced us to upgrade Hardhat, and Hardhat changed implementation of fork chain. They rewritten it from TypeScript to Rust. And now this implementation, like, you cannot dynamically change chain ID, because chain ID is just in some internal variable in Rust, and there is no setter for it. So actually now, to have multiple chains, we need to deploy backend per chain, whereas historically we just had one Lambda, and when it was getting request, it was like setting chain ID and running stuff.
Well, what do you use it for? For compilation only?
Which one?
Hardhat.
Yeah, like so Hardhat is the component which is capable of spitting out this file. Because this file will not come from Alchemy. Alchemy has no interest in sending you.
Isn't this the typical output of debug trace?
Yeah, if you run archive node on your machine and you configure it to support debug namespace, you will have access to this RPC. But like we are using free Alchemy account for this, and I don't even know at which plan Alchemy supports debug namespace.
Okay.
So for free account, you will not get debug namespace. So this is this trick that we do. Hardhat has this feature of forking other chains. So what it's capable of doing, it can like fetch the part of state of a chain that it requires using some RPC calls directly to RPC.
I was just asking because if there's an issue with Hardhat, why don't you use Foundry?
I don't know if Foundry even has forked chains. I haven't looked into Foundry.
Well, it's Anvil, I guess, but it does, and I believe it's like more up to date.
Well, so I think the answer is we started this project back in 2020. So
Yeah, like,
Foundry
Well, I
didn't exist.
understand why you started with
Yeah.
hardware. I'm just thinking about any idea how to solve your issue.
No, the issue is really easy. It's just like it would probably take me a few hours to solve it, but it was very last minute. And when you come back here in a week, you will see Polygon, Sepolia, and yeah, Polygon, Sepolia. I forgot what is Polygon testnet now because Mumbai is off. No.
After Mumbai?
Yeah. Now Mumbai is off as well. So so we have Polygon and Ethereum and testnet for these, and we can actually support many more, but you know, probably in future. Like when we work on some chain, we kind of add it. But if someone asks us and we know how to get RPC, we add it. But for example, with Arbitrum, we wanted to add Arbitrum, but it was complex. It doesn't work well with this hard hat forked environment for some internal reasons. So yeah, but the plan for this tool is to support much more networks, and some networks are easy to add because if it's just compatible, we just pretty much configure infrastructure and RPC URL. But with other ones, we need to do some custom stuff as well. So for instance, when ending a chain, we need to configure the blocks for hard forks because we are like we need to tell this fork node when certain formats are changing, because as hard forks were being done, different EVM instructions have been available and not. So yeah, it's a few hours of work really, but it's work nevertheless. So we haven't done it yet. So what else? Yeah, so other things which I haven't covered, tracing biggest offender of gas usage. Actually, I covered this partially. So there is this heat map where the biggest square is the one you should click and you see where the gas is used. And then there is this another thingy in here, in this quick links. So in quick links you have from gas cost. So you have like listed here the most expensive instructions. So for example, this storing to a state, you see that, for example, this line costs you 2,900 gas. So you can just, like, if you come here to optimize your gas usage, like probably good idea is just to go through like list of these and then think of which of them are necessary and which of them you could maybe do something different. Like for example, this log4 costs almost 2,000 gas. Like, do we really need all these parameters? Maybe we don't. Like this is kind of questions you can ask yourself. Inspecting internal function call parameters. I did speak about this. So what I mean is like you have the coded parameters here, both for like a jump test is a it's an internal function, right? So it says internal pure, so you can see parameters of this. Tracing dependencies within transaction. So this is about like this contract calls into this contract, which then calls into this contract, and so on. So on Etherscan you only see the topmost call, whereas here you see entire tree. Inspecting source code and bytecode of smart contract. Yeah, I showed this part. Right. So if you find this helpful, please join our Discord. You can scan it or find it on our page. There's actually a little bit of hidden agenda. Well, not hidden anymore. There's a little bit of agenda for me with this. So when we applied for a grant for Ethereum Foundation, they told us we only give grants to projects which have built community. So that's what we're doing with this. We are building community. So the more people we have on our Discord, the better argument we have for getting funds from Ethereum Foundation. I promise not to send you any crypto scams or memes or whatnot. It's professional and nice. And yeah, this is all I prepared for today. And thank you very much for listening. It was a pleasure.
Sorry, one more question.
Yeah.
What are your plans in terms of monetization or open sourcing the project?
No. Well, open sourcing pretty well. So it's like if we get funded by Ethereum Foundation, this is really on the checkbox, and we really got stuck with lawyers about the license. Like we probably shouldn't. Listen, this is an advice. If you want something fast, don't ask your lawyer. So I did a mistake of asking a lawyer, and now I'm kind of stuck with a license thingy. I probably should have just done it myself. So this will probably be open source at some point. Monetization, I don't really see it. I see it more like a passion project, and maybe it's a little bit like kind of helping brand of Rumblefish, which is like software development company. So the thought process is like, if there are people coming to our webpage and domain, it helps our, I don't know, like search position. But I don't really see it as a paid tool. And I mean, we use so many open source stuff, so I think it would be problematic. I don't even know if you can use Hardhat in this way for commercial use. Yeah, it's a passion project. Yeah.
Like I think it should be open source if you want to have any like user adoption.
Yeah.
First point. Second point, with Ethereum Foundation, we actually get a grant from them, but it was 2016.
Mm-hmm.
And they are like more now trying to disappear. That's their like mission statement. But also they recommend like ask grant from anyone else.
Okay.
And we got a grant for Tulink in 2022, for example, from Coinbase. It was a quite a big grant, so just like don't rely, I would say, on Ethereum Foundation. They don't really give too many grants right now, but the ecosystem gives grants. So if you open source that and ask around,
Yeah.
you'll definitely get
So
grants.
one reason why I was a little bit, not sure about open sourcing this. I mean, we will do this anyway, but kind of a challenge is that there is extensive backend to it, and this backend is very much serverless kind of backend. So all these like extracting debug trace and supporting 30-something version of Souls. Like this is lambdas and step functions and SQS queues and whatnot. So this is not something that you can expect to run on a developer machine, but it needs to be like this. Like, listen, installing Souls is like 200 megabytes. If you multiply it by 30, you have 6 gigabytes, or it's crazy. So it's really something you need to do in the cloud, and these data sets are way too big to operate on a normal computer. But yeah, like I think we will open source it.
But I think it's not against open sourcing is for transparency. So you can open source that, but still, of course, folks will be using like your hosted version, but it will be like open source hosted
No,
version.
it's more like a developer experience. Like for instance, like Bartek, who develops this stuff, like he's one of members of my team. Like he actually tests on Lambda, so he deploys it on AWS account and tests it there. It's not really something that you comfortably can run on your laptop. Like we don't have.
There is that, I can't remember the name, but there is that toolkit that simulates.
Yeah, it has 10% of AWS services, and we are using more.
Okay.
So it's for very simple stuff.
What was the name of that?
It's serverless local, I think, or some local.
Something local.
Some local, yeah.
Something local.
So some is serverless application model. So some local is doing this. So yeah, what we are trying to do with grants, really, like we are looking for chains that are, not Polygon and Ethereum, and they would be like to be included in this. So maybe, some chains that are EVM compatible, because like really, if a chain is, providing RPC, like we can run this fork chain using their RPC, and pretty much maybe they are not using scan. Maybe we need to adapt a little bit API call to fetch source code, or stuff like this. But it's a probably not huge effort for us to add multiple chains in here.
I think look at the base grants they are willing to really.
Base grants. Yeah, this is probably a very
It's
good.
called local stack.
Local stack, that's the one. Yeah, you're right. So yeah, you will not run this on local stack. It's way out there.
All right.
It's just like when you know how to use different AWS. Like in reality, like we could probably write it in Rust, but it would take much more time.
Just forget it.
Yeah.
I get the point.
Yeah. No, but yeah, we will open source it someday. I was even thinking for this presentation that I will tell the moment we hit 100 people on Discord, we will open source it. I was kind of having this joke loaded, but then I can see we are not hitting this target today. I think we have like maybe 24 people on our Discord at the moment. But I'm giving this presentation in Split and in Belgium throughout like next 2 months. So things will start moving, I suppose. Okay, thank you guys again. Thank you for listening.